So first let us discuss the code for the last week's lab assignment, which is depth first search traversal using adjacency matrix, right? The graph should be represented through an adjacency matrix and on which you should perform depth first traversal, both using recursive logic and also with non-recursive logic. So here is the code. So some part of the code we have discussed in the last class itself. So this is the adjacency matrix of size 100 by 100, and we are using stack here, and there is an array visit which is used to represent whether the nodes have been, whether the vertices have been visited or not. We contain the number of vertices, and these two variables are for maintaining the stack. So this is to push an integer to a stack. If TOS is less than max size, then we can push. Otherwise, we'll say that stack is full. Okay. So our stack size is 100. Okay. And this is the pop function. TOS is -1, it will say stack is empty, otherwise it will return the top of the stack. And this is the function to create graph. Here we ask the user to enter the number of vertices in the graph. Okay. And then what are the vertices? Then we read the adjacency matrix as the input. Okay. So then the max size is stored in V. So this is the max size. Max size of array is V. Okay, not 100. It will be equal to number of vertices. And this, using this loop, we read input for the adjacency matrix. Okay, that is the entire graph will be represented as an adjacency matrix. The adjacency matrix will have this many rows and this many columns, V rows and V columns. This is to display the graph as adjacency matrix. And this is the function initialize visit, which initially sets visit value for every vertex as 0. And this is the DFS logic for this is an iterative logic, that is non-recursive logic for DFS. Okay, so non-recursive can also be called as iterative logic. DFS logic for so here we are declaring some variables. I initially row is set to 0, column is also set to 0, and initialize visit, that is for every vertex we set visit as 0. And first we are visiting the vertex 0, that is the root node. We are visiting, visit of 0 is set as 1. And then this is an infinite while loop. If you observe, the logic is similar to what we implemented in adjacency list, but you have to just convert it to adjacency matrix type. Okay, so visit of 0 is made as 1. For remaining all the vertices, the visit will be 0 right now. Okay, row is 0 and column is also 0. Then we are taking x is equal to adjacency matrix of row and column. Okay, so what is the adjacency matrix value of row comma column? That's what we are checking. So this will be, so this is what this is. Say for example, in adjacency matrix, yeah, if you have this, say this is 0 1 0 1 0 1 0 1 0, something like that. I'm not writing any meaningful thing. Okay, but adjacency matrix contains either 1 or 0, right? If it is a 0, it means there is a link. Sorry, if it is a 1, it means there is an edge. If it is a 0, there is no edge. And one thing you can be sure that these diagonal edges will be always 0, because we are not considering self edges. So this, if you see, row is 0. So this is row, right? I mean, so row is 0 and column is also 0. So that is, it means row and column are same, means it's a diagonal entry. So surely this x will be what? 1 or 0. X will be 0. Okay. So here this condition will not be satisfied. Okay, and column, then else part it will check whether column is equal to V. Column is not V. Currently column is 0. V is the number of vertex or the number of rows or number of columns. Okay, both are all are same, right? So now what should we do? See, actually now we have to increment column. In this case, we have to increment column. It's not going down. I don't know. Yeah, in this case, we have to increment column. So these two cases where it has not satisfied these two cases. So column will increment. If column increments, then column will become 1. Row is still 0. Row is still 0 and column is 1. So now row is 0 and column is 1. So what is that? It may be 1. Okay. If there is a link from 0th vertex to, if there is an edge from 0th vertex to first vertex, then this will be 1. Okay. If x is equal to 1 and column not equal to V. See, V is, this is what the number of vertex. So the number of rows will be V, number of columns will be V. But actually the column number and row number starts with 0. So the last column number will be V minus 1. Similarly, the last row number will be V minus 1. Okay. So there is nothing on V. So if it comes to V, you have to stop, so that we are checking this. If column not equal to V and visit of column, and if that vertex is not yet visited. So three things you have to check: whether there is an edge or not, whether column has not reached beyond the boundary, and whether that vertex has not reached, not yet visited. Okay. So everything represents a vertex, right? So column also represents some vertex. So if that vertex is not visited, then visit that vertex. That is, display that and make it as 1. Visit of column equal to 1. So now we should jump to this particular row. So this is first row. Now the algorithm should jump to this row. Okay, we started with 0th row. Now we have to jump to first row. But again, you may have to come back to 0th row. So you have to push this row number into stack. So what we are doing, push of row, push that row number, and now previously whatever the column, that will become row, because now we have to move to this row. Okay, and from this row we have to start with 0th location. So column becomes 0. So this is the core logic. This is what I think you should understand. But this is similar to the same adjacency list thing. Okay, there we used pointer, here we are using array. That's it. Okay. Suppose if column has reached the lost beyond lost location, then what should we do? Then we should pop. Then we should pop, and whatever you pop, that will become the current row, and again column will be 0. Okay. Suppose when you pop, if you get -1, then you have to break. That is the time at which this while loop will end. Okay. Otherwise, column plus plus. So this is the logic for what you call. This is the logic for non-iterative depth first search using adjacency matrix. Okay. And this is the logic for iterative one. Okay. So this is the logic for recursive. This is the logic for recursive. That is the logic for iterative and non-recursive. So this is the logic for recursive. Here we are defining a recursive DFS. We are passing the row number. So initially it will be 0. We'll be passing 0. That is the root node. And then we check whether the root node is visited or not. If it is not visited, we are displaying it and we are visiting it. Then we are starting with you are passing what row number of the root node. Okay, so we have to pass through the column. So for column equal to 0, column less than V, column plus plus, the actual concept is same, but here push and pop will be automatically taken care. We need not write explicitly. So again we take this x is equal to adjacency matrix of row comma column. If x is equal to 1 and visit of column is equal to 0, then what we do, there we check the three conditions. What? And column not equal to V, that also we have checked here. But here it is a for loop. That for loop ensures that column will not go beyond V. Okay. So if x is equal to 1 and visit of column equal to 0, then we visit that, we display that. Okay. Then we display that. After displaying, what should you do? You should move to the next row. You should move to this particular row. Whatever the column number says, that row we should move. So which means what? Again, you call recursive DFS by pausing column. So previously, what is the column? Now that will become the row and continue the process. Okay. Column plus plus will be taken care of by this. Incrementing column, this will take care. And suppose if column has reached V, then return will be automatically taken care. Okay. Because it's a function call, right? So that is the recursive logic. Okay. So the execution we have already discussed, right? So in today's class, what we are going to discuss is something called as topological sort. So actually topological sort can be performed only on a directed graph without cycle, which means it's a tree. Okay, you can perform topological sort only on a graph without cycle. Okay, it may be directed or it may be undirected, but here we are taking directed graph. Okay, let us assume that will be working on a directed graph. Okay. So remember this, there should not be any cycle. If cycle is there, you cannot perform topological sorting. Okay, and so let us assume this is the graph or tree for which you need to perform topological sort. So actually it is a tree. There is no cycle here. It looks like a something as if having cycle, but if you check the edges, all these edges are directed. There is no edge. There is no cyclic edge, right? Okay. So this is the tree or this is the graph without cycles. Okay. Now you have to identify the vertex. The first job is to identify the vertex whose in degree is 0. Could you tell which vertex in degree is 0 here? Is there any such vertex? First you have to check. Is there any such vertex whose in degree is 0? Yes. Is there any vertex in this graph whose in degree is 0? Yeah, 32. Good, good. V0. Yeah, V0 in degree is 0. The in degree of V0 is 0. For right now, for all other nodes, for all other vertices, they don't have 0 in degree. Okay. So this is where the algorithm starts. At any point, if you are unable to identify a vertex with 0 in degree, at any point, if you are unable to identify a vertex with in degree 0, then you have to stop the algorithm and you have to say that the particular graph contains cycle and topological sort cannot be done. Okay. So identify the vertex whose in degree is 0. This is that vertex. So just display that. Okay. Or visit that. After visiting that vertex, what you should do in the sense, now delete all the edges that were going out of from V0. Delete all the edges that are going out from V0. What are the edges starting from V0? Delete all the edges that are starting from V0. What are the edges that are starting from V0? How many edges are arising from V0? 3 edges. What are they? What are those 3 edges? What are the 3 edges that are starting from V0? No, edges. How will you represent edge? What are the 3 edges that are starting from V0? There are 3 edges, right? One is V0 to V1. This is one edge. Okay. Another one is V0 to V3. Another one is V0 to V2. And the last one is V0 to V3. So all these edges you have to delete. So yeah, V0 to V1, V0 to V2, and V0 to V3. So delete all these edges. Delete this edge, delete this edge, delete this edge, delete V0 also. delete V naught also. Delete V naught and all its outgoing edges. So once you delete V naught and all its outgoing edges, the graph will now look something like this. Okay, tree is also a graph, so I can call it as graph. Okay, so the graph is now something like this. Now, you from this graph you have to identify the vertex with 0 in degree. So now, how many vertex have 0 in degree? Now, how many vertex has in degree of 0? Yes, three vertices. What are they? Which are the vertices has 0 in degree? Yes, Rupa. Which are the vertices? Which are the vertices? Which vertices has 0 in degree? V1, V2, V3. Yes, good. V1, V2, V3. From these, you pick any one vertex. Okay. So this is the one peculiarity of topological sorting. See, the output sequence need not be one common sequence. The output sequence may vary. Please note down this point. So now we can pick up any vertex whose in degree is 0. So we can pick up either V1 or V2 or V3. Okay. Let us say we are picking up V3. So when I pick up V3, it means I'm visiting V3. So let me display V3. V3 is displayed. After displaying V3, what you should do in the sense, delete V3 and all the outgoing edges of V3. How many outgoing edges are there in V3? From V3. How many outgoing edges are there from V3? 2. What are they? What are they? What are the 2 outgoing edges from V3? Yes, Mahita. V3 to V4 and V3 to V5. So delete this 2 edge. So delete this edge. Okay. Delete this edge and delete V3 also. Delete V3 also. Okay. So after this, now this is the state of the graph. Okay. So now how many vertices are there with 0 in degree? Now how many vertices are there with 0 in degree? 2 vertices. What are they? Which are the 2 vertices? Which are the 2 vertices which has 0 in degree? V1 and V2. Okay, yes, good. So we can pick up anything, either V1 or V2. Let us assume we are picking V2. So after V3, we will display V2. So after V3, we will display V2. So now you have to delete all the outgoing edges from V2. So what are the outgoing edges from V2? Or how many outgoing edges from V2 is there? How many outgoing edges we have from V2? Yes. From V2, how many outgoing edges we have? Yeah, we have 2 outgoing edges, V2 to V4 and V2 to V5. Yes, delete these 2 edges. Yes, good, Rupa. So delete these 2 edges and delete this vertex also. Okay, right? So now this is the resultant graph you got. Okay, right? This is the resultant graph you got. Okay. Now, so now you see. So now how many vertices are there with in degree 0? 2 vertices. What are they? What are they? V1 and V5. Okay. So let us say that we are visiting V5. So let us say that we are picking V5. So visit V5. So after V2, we visit V5. Okay. V5 does not have any edges. So there is nothing to delete. So if you only delete the vertex V5, so the resulting graph will be something like this. Okay. Right. Now how many vertices are there with 0 in degree? Now how many vertices are there with 0 in degree? Only one. What is that? What is that? Which vertex? Which vertex has 0? Only V1. Only V1 has 0 in degree. Okay. So let us, so we have no option, only V1 you have. So we have to consider V1. So start with V1. Okay. I mean visit V1 and delete all the outgoing edges from V1. How many outgoing edges are there from V1? How many outgoing edges are there from V1? Only one, that is V1 to V4. So delete this edge and also delete V1. Okay. Now the resultant graph is only V4. There is only one vertex V4. Okay. There is no other vertex. Just visit this vertex V4 and delete it, and delete that vertex also, right? So that's it, the algorithm says. So now the sequence is what? This is the sequence. So this is the topological sorting order: V0, V3, V2, V5, V1, and V4. Okay. But this is not the only order. Say for example, initially we should start with V0. There is no other option. Okay. Initially we should start with V0 because there is only one vertex we have with 0 in degree. Now from here we can pick up either V1, V2, or V3. Okay. So assume that in the second case we are picking up V2. If we pick up V2, then what will happen? After V0, V2 we will visit. Then we will delete which edges? If we pick up V2, then we will be deleting which edges? What are the outgoing edges of V2? So what I'm trying to explain in the sense, the algorithm will not have only one output. The output may vary. That depends on your style of implementation. Yes. Yes, Rupa. Good. V2 to V4 and V2 to V5. Okay. So if you say, let us assume we are deleting these two edges, and also we are deleting V2. Okay. Now what will be the resultant graph? Now the resultant graph will be, yes, this. So let me draw here. V1 we have, okay. We have V1. So we'll have V1 and V1 to V4 we have, okay. V4 we have. We don't have V2. We have V3 and we have V5. Okay, we have V5, right? So we have so all these are directed edges because it's a directed graph. We have an edge from V3 to V4 and we have an edge from V3 to V5. Okay, right. Fine. So now from this graph, how many vertex are there which has 0 in degree? Now how many vertex has 0 in degree? 2. What are the vertex? What are the vertex? Which are the vertex? V1 and V3. Okay. So now you can visit either V1 or V3. Okay. Let us assume that we are visiting V1. Okay. Say I am visiting V1. So if you visit V1, then we have to delete the edge which is going out of V1. How many edges are going out of V1? How many edges are going out of V1? 1. Yes, 1. Yeah, Rupa. So that is V1 to V4. So delete that edge and delete this vertex. Okay. So this is the resultant graph. So in the resultant graph, we have what? We have V4, V3, V4, and V5. Now how many vertex are there with 0 in degree? Now how many vertex are there with 0 in degree? Only one. Yes, good. What is that? What is that? V3. So there is no option. We have to visit V3. So visit V3 now. After visiting V3, you have to delete the edges, outgoing edges of V3. So what are the outgoing edges of V3? What are the outgoing? How many outgoing edges from V3 we have? 2. Yeah, V3 to V4 and V3 to V5. Good. So delete these two edges. Okay. So delete these two edges and delete V3 also. So resultant, what we'll have just two nodes V4 and V5, which is not connected. Okay, we have two vertices V4 and V5. Now how many vertices are there which with 0 in degree? Now how many vertices are there with 0 in degree? 2. What are they? What are they? V4 and V5. Okay. We can visit them in any order. We can visit either V4 first or V5 first. So let's say let me visit V4 first. Then delete this. Then visit V5 and delete. Okay. So like that, there may be different orders of output. Okay. It all depends on your implementation, right? So this is what the assignment which you are supposed to do. So you can represent the graph uh, any way. Okay, we have discussed several ways of representing the graph. I'm not going to give any restriction that you have to represent in this way or that way. You do in your own way. Okay, so that for evaluation also we have multiple options. So I want different people to try different way. Okay, right? But anyway, I'll show you the output of this. I'm not going to tell you like how I have implemented or what method of implementation I followed. You can follow anything, okay? Any simple method or any complex method, that is up to you. So nano toto.c. This is the code. I'm not going to show you the code, okay? I'll just show you the execution. GCC -o slash toto. Enter the number of vertices. So let us take that graph itself. So, but you consider is a directed graph. Okay, this graph contains how many vertices? 3, 5, 6 vertices. So 6, and enter the number of directed edges. How many edges are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 edges. Of course, from my output, you can understand to certain extent the style of implementation. But you need not follow the same style. You may even use adjacency list or adjacency matrix or whatever you want. Now we are asking to enter all the edges. So what are the edges from 0? We have 0 to 1, 0 to 2, and 0 to 3. Okay. So 0 to 1, 0 to 2, 0 to 3. From 1, we have only one edge, 1 to 4. 1 to 4. Okay. From 2, we have two edges, 2 to 4 and 2 to 5. 5. From 3, we have two edges, 3 to 4 and 3 to 5. This is the output 0, 3, 2, 5, 1, 4. This is the first style which we have discussed. Okay. So first it is visiting 0, then 3, 2, 5, 1, and 4. Okay. So that is the books, I mean the slide style 0, 3, 2, 5, 1, 4. Right. So that's it. That's it for the day. Okay. If you have any doubts, you can ask. So here I'm sharing the Google form link. You can fill it up. So this will be the last lab assignment. We will not be having any further lab assignments. Okay. We'll be having next quiz on Monday. That will be our last quiz.